I welcome everyone to this new video that explains the chapter Chemical Bonding and Molecular Structure from Class 11 CBSE. In this chapter, we will find the answer for some common questions of chemistry such as why do atoms combine, why are only certain combinations possible, why do some atoms combine while certain others do not, why do molecules possess definite shapes. To answer these questions, scientists have been constantly developing many theories. In this chapter, let us look some theories among them. Before diving into the chapter, we need to understand that the attractive force which holds various constituents together in different chemical species is called a chemical bond. First, let us discuss about Coastal-Lewis approach to chemical bonding. In 1916, Coastal and Lewis succeeded independently in giving a satisfactory explanation about the formation of chemical bond in terms of electron. Lewis pictured the atom in terms of a positively charged kernel and the outer shell electron that could accommodate a maximum of 8 electrons. He further assumed that these 8 electrons occupy the corner of a cube which surrounds the kernel. Here, kernel means the nucleus plus the inner electron. Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. In the formation of a molecule, only the outer electrons take part in chemical combination, and they are known as valence electrons. The inner shell electrons are well protected and are generally not involved in the combination process. G.N. Lewis, an American chemist, introduced the symbol notation to represent valence electron. The number of dots around the symbol represent the number of valence electron. The number of valence electron helps to calculate the common group valence of the element. The group valence of the element is generally either equal to the number of dots in Lewis symbol or 8 minus the number of dots or valence electron. Coastal, in relation to chemical bonding, drew attention to the following facts. The noble gas separate the highly electronegative halogens and highly electropositive alkali metals. The formation of negative or positive ions is associated with gain or loss of electron by the respective atom. The negative and positive ions thus formed attain stable noble gas electronic configuration. The noble gas have a particularly stable octet configuration of Ns2np6 except that of helium which has duplet configuration. The negative and positive ions are stabilized by electrostatic attraction. For example, in the formation of NaCl, the sodium loses one electron to reach electronic configuration of neon. In the same way, chlorine gains an electron to reach stable electronic configuration of argon. Similarly, in the case of CaF2, the calcium loses 2 electrons to reach argon's electronic configuration and each fluorine gains 1 electron to reach stable configuration of that of neon. The bond formed as a result of electrostatic attraction between the positive and negative ion was termed as the electrovalent bond. The electrovalence is thus equal to the number of units of charge on the ion. From the above example, we can say calcium is assigned a positive electrovalence of 2 while chlorine a negative electrovalence of 1. Coastal's postulation provides the basic for the modern concept regarding ion formation by electron transfer, formation of ionic crystal compounds, and helped in understanding and systemization of ionic compounds. But he did not recognize the fact that a large number of compounds did not fit into this concept. Coastal and Lewis in 1916 developed the electronic theory of chemical bonding. According to this, atoms can combine either by transfer of valence electron from one atom to another or by sharing of valence electron in order to have an octet in their valence shell. This is known as Octed Rule. Now let us talk about an important refinement in the Lewis theory made by Irving Langmuir in 1919. While Lewis introduced the concept of electron sharing in covalent bond, Langmuir took it a step further by abandoning the old idea that electrons are arranged in a fixed cubical shape around the atom. Instead, Langmuir introduced the term covalent bond. For example, in the formation of Cl2 molecule, the chlorine atom with electronic configuration Ne3s23p5 is one electron short of the argon configuration. When two chlorine atoms with this electronic configuration combine, they share one of its electrons with the other. Thus, both chlorine atom attains noble gas configuration. This bond is generally called a covalent bond. This can be represented by LeDo Structure. where dots represent the valence electron. Lewis dot structure can be drawn for all kinds of molecules, whether the atoms involved are identical or different. The key principle to remember for covalent bond are: each covalent bond is formed when atoms share a pair of electrons. Each combining atom contributes at least one electron to the shared pair. The goal of both atoms is to achieve the outer shell electronic configuration of noble gas by sharing electrons. In some molecules, atoms only share one pair of electrons, which we call a single covalent bond. This is the case of Cl2. But in other molecules, atoms share 2 or even 3 pair of electrons. When 2 pairs are shared, as in the carbon dioxide molecule, we have the Lewis dot structure provides a picture of bonding in molecules and ions in terms of shared pair of electrons and the Octet Rule. While Lewis dot structure might not explain every detail about a molecule's behavior, they give us a strong foundation for understanding the formation and properties of molecules. So, how do we write this Lewis dot structure? First, we need to figure out the total number of valence electrons available for bonding by adding all the valence electrons in the molecule. For example, in methane, carbon contributes 4 valence electrons and each hydrogen contributes 1. That gives us a total of 8 electrons for bonding. If we are dealing with ions, we have to add 1 electron for each anion and subtract 1 electron for each cation from the total number of valence electrons. For example, carbonate ion, the 2 minus charge tells us to add 2 extra electrons. In contrast, the ammonium ion, NH4 plus, has a positive charge, so we subtract 1 electron. Knowing the chemical symbols and the typical bonding patterns of the atoms help us guess the skeletal of the molecule. The atom that attracts electron comparatively low, that is least electronegative atom, usually occupies the central position in the structure. For example, in NF3, nitrogen is the central atom, while more electronegative fluorine atoms are on the outside. In CO3, the carbon sits at the center and the oxygen atoms are arranged around it. Once we distribute the electrons as bonding pairs between atoms, the remaining electron pairs are either utilized for multiple bonding or remain as the lone pair. The basic requirement being that each bonded atom gets an octet of electrons. Lewis dot structure are a way to show how atoms share or exchange electrons to form molecules. They are like a map of where the electrons are, but they don't tell us what the actual shape of the molecules look like. The formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of valence electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in a Lewis dot structure. That is, formal charge is equal to total valence electron in free atom minus total non-bonding electrons minus half of total bonding electrons. We must understand that the formal charges do not indicate real charge separation within the molecule. Formal charges help in the selection of lowest energy structure from a number of possible Lewis structures for a given species. Generally, the lowest energy structure is the one with the smallest formal charge on the atom. The formal charge is a factor based on pure covalent view of bonding, in which electron pairs are shared equally by neighboring atoms. The Octed Rule is useful for understanding structure of most of organic compounds and mainly applies to second period elements, but still it has 3 types of exceptions. Number 1. Incomplete octet. In some compounds, especially those with elements having less than 4 valence electrons, the number of electrons surrounding the center atom is less than 8. This occurs in the compound of LiCl, BeH2, BCl3, AlCl3, BF3. Odd electron molecule. In molecules with an odd number of electrons like nitric oxide, NO, and nitrogen dioxide, the Octet rule is not satisfied for all atoms. In some compounds, there are more than 8 electrons around the center of atom. This is termed as expanded octet, and this occurs because element in and beyond third period of the periodic table has 3d orbital also available for bonding, and this increase valence electrons. Some of the examples of such compounds are PF5, SF6, H2SO4, and a number of coordination compounds. Interestingly, sulfur also forms many compounds in which the Octet rule is obeyed. Example, sulfur dichloride. Now let us look some drawbacks of Octet rule. The Octet rule assumes noble gases don't react, but some of them like xenon and krypton form compounds like SeF2, KrF2, etc. The Octet rule doesn't tell us the shape of the molecule. It does not explain why some molecules are more stable than the others. To form an ionic bond, the metal atom loses an electron to become a positive ion, while the nonmetals gain an electron to become a negative ion. Once the ions are formed, they come together to form a stable crystal lattice. For example, sodium ions and chloride ions combine to form sodium chloride or table salt, which has a highly ordered 3D structure held together by strong electrostatic forces, also called Coulombic interaction. Now you might wonder, does it always take energy to form these ions? Yes, removing an electron from sodium requires energy, and gaining an electron by chlorine releases energy. But even if the total energy of forming the ion is positive, the crystal structure is stabilized by the energy released when the lattice forms. This is called lattice enthalpy, and it compensates for the energy required in forming the ion. When we write a clear definition, it can be as: the lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. For NaCl, the lattice enthalpy is 788 kJ per mole, which means that 788 kJ of energy is needed to pull apart the solid NaCl into Na plus and Cl minus ions. The stronger the attraction between the ions, the higher the lattice enthalpy. Now let us look at the bond parameters. Number 1. Bond length. It is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. In case of covalent bond, the contribution from each atom is called the covalent radius of that atom. Each atom's covalent radius contributes to the bond length in a covalent bond. The covalent radius is half the distance between two identical atoms connected by a bond. To find the bond length, we add the covalent radius of the two atoms. The van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bounded situation. For example, in chlorine, the van der Waals radius is 180 picometer, while the covalent radius in a bonded pair is 99 picometer. Bond length also depends on the type of bond. Single bonds are longer than double bonds, and triple bonds are shortest. This happens because multiple bonds bring atoms closer together. Bond angle. It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ions. It is measured in degree and can be determined using spectroscopy. The bond angle helps us to understand the spatial arrangement of atoms and the overall shape of the molecule. For example, in water, the bond angle is 104.5 degree. Bond enthalpy. Bond enthalpy is the energy required to break 1 mole of bond between two atoms in a gaseous state, measured in kilojoules per mole. For instance, the bond enthalpy of H2 is 435.8 kJ per mole, meaning it takes this much energy to separate H2 into individual hydrogen atoms. Stronger bonds have higher bond enthalpies like N2 with 946 kJ per mole. In molecules with more than one bond type, such as water, we use the average bond enthalpy due to difference in bond strength within the molecule. Bond order. In Lewis theory, bond order is the number of bonds between two atoms in a molecule. For instance, H2 has a bond of 1 as it has single bond. O2 has a double bond as its bond order is 2, and for N3 it is 3. Higher bond order indicates stronger bonds and shorter bond length. For example, N2 with a bond order of 3 has one of the highest bond enthalpies among diatomic molecules. Interestingly, molecules that are isoelectronic also share the same bond order. Sometimes a single Lewis structure isn't enough to represent a molecule accurately. Take ozone as an example. In its two possible structures, we see one single OO bond and one double OO bond. Yet experimentally, The bond lengths are identical at 128 picometer between a single and double bond length. This leads us to resonance. Resonance occurs when multiple structures called canonical forms together represent a molecule better than any single structure. These forms are combined into a resonance hybrid that accurately depicts bond characteristics. In O3, the hybrid structure stabilizes the molecule by averaging bond properties, making it more accurate and lower in energy. Not all covalent bonds are the same. In a non-polar covalent bond, like in H2 or O2, two identical atoms share electrons equally. But in a polar covalent bond such as HF, the shared electrons are pulled closer to the atom with higher electronegativity. This creates a dipole moment, a separation of charge that gives the molecule a partial positive end and a partial negative end. The dipole moment is calculated by multiplying the charge by distance between the charge. In chemistry, we often use Debye units to measure this, honoring Peter Debye, who studied molecular polarity. The dipole moment in HF can be represented with an arrow pointing towards the more electronegative atom, fluorine. In molecules with multiple bonds like H2O, the dipole moment adds up, creating a net dipole moment due to its bent shape. But in linear molecules like BeF2, the dipole cancels each other out, resulting in zero net dipole moment. An interesting case is ammonia and nitrogen trifluoride. Both have a similar pyramidal shape. However, NH3 has a higher dipole moment than the nitrogen trifluoride. Why do you think this happened? If you know, comment it below, or else I will say it. It is because in ammonia, the lone pair dipole points in the same direction as the NH bond. But in nitrogen trifluoride, the lone pair points opposite the N of bond, reducing the overall dipole moment. In brief, the size and charge of atoms, their arrangement and the nature of bonds all contribute to dipole moment in a molecule. Just as covalent bonds can have some ionic character, ionic bonds can have a bit of covalent character. Pajan's rule helps us to predict how much covalent character an ionic bond might have. Size of ions. Smaller cations and larger anions make the bond more covalent. Higher charges on the ions increase covalent character. Transition metals create more covalent character than alkali metals because they polarize more. So polarization occurs when the cation attracts the anion electron, increasing electron density between them, making them more covalent. VSEPR or valence shell electron pair repulsion theory explains that electron pairs around a central atom repel each other and arrange themselves as far apart as possible. This arrangement minimizes repulsion, creating specific shapes. The main principles are: the shape of a molecule is determined by the number of valence shell electron pairs around the central atom. Electron pairs repel one another because they are negatively charged and they want to be as far apart as possible. Lone pairs take up more space around the central atom than the bonding pairs, which is increased repulsion. The order of repulsion strength is an important concept. Now let us look at that. Lone pair repulsion is the strongest. The lone pair bond pair repulsion, and finally the bond pair repulsion is the weakest. Now let's see how VSEPR predict molecular shapes. If a molecule has no lone pairs on the central atom, it usually follows the basic geometries. For example, two bond pairs make a linear shape like CO2, while three bonds make a trigonal planar like BF3. Four bond pairs make a tetrahedral shape as in CH4 with bond angles around 109.5. When lone pairs are present, they push bonding pairs closer together, changing the expected shape. Water, for example, water has two lone pairs which push the bonding pair closer, making bent shape with a bond angle of about 104.5 instead of 109.5. Another example is ammonia, which has one lone pair. This gives it a trigonal pyramidal shape with bond angle around 107. While VSEPR theory is effective for predicting shapes, it does not have its limit. For instance, it doesn't explain why electron pair repel in such specific ways or exact energy difference between shapes. So, we know that Lewis structures show us how atoms bond, but they don't explain why bonds differ in strength or length. For instance, in H2 bond, energy is 435.8 kJ per mole with bond length of 74 picometer, while F2 has just 155 kJ per mole bond energy and a 144 picometer bond length. Also, it doesn't predict molecular shapes for larger molecules like methane or NH3. To fill this gap, we look at quantum mechanics with two main theories, valence bond and molecular orbital theory. Let's start with the valence bond theory. Imagine two hydrogen atoms combining closer. Each has a nucleus and an electron, and initially they don't interact. But as they get closer, attractive forces start pulling them together. The nucleus of one atom attracts the electron of the other. At the same, there are repulsive forces from the nuclei and the electron pushing them apart. Eventually, a balance is reached where attractive forces dominate, energy is minimized, and a stable bond forms. This distance becomes the bond length. According to valence bond theory, bonding happens when orbitals overlap and electrons with opposite spin pair up. Greater overlap creates stronger bond. In height too, this overlap happens between two oneness orbitals, but in complex molecules like CH4, overlap happens between hybrid orbitals. Now bonds differ on how orbitals overlap. A sigma bond forms from head-on overlap such as SS or SP overlap, which is strong and forms along the bond axis. A pi bond forms from side-by-side overlap of p orbital and is generally weaker. In multiple bonds, sigma bonds form first and then pi bonds are added. Overlapping also explains molecular shapes. For example, in CH4, carbon's orbital hybridize to form a tetrahedral shape with 109.5 degree bond angles. This directional nature of orbitals explains the 3D shapes of molecules, which symbol LeDo structure called. In short, valence bond theory gives us a clearer picture of why bonds form, their strength, and how atoms arrange in space. We will dive deeper into bond types and hybridization next to see how these overlap ideas shape more complex molecules. Hybridization is a concept introduced by Linus Pauling to explain molecular geometry. Hybridization occurs when atomic orbitals combine to form new equal energy orbitals called hybrid orbitals. These hybrid orbitals help atoms bond in ways that reduce repulsion between electrons, creating stable shapes. The main features of hybridization are number of hybrid orbitals equal to the number of atomic orbitals combined. All hybrid orbitals have the same energy and shape. Hybrid orbitals form stronger bond than the pure orbitals. The type of hybridization tells us the molecular geometry. Now let's explore different types. First is sp hybridization, involving one s and one p orbital, creating two sp orbitals. These arrange in a linear shape with a 118 angle. An example is beryllium chloride, which has this linear arrangement due to its sp hybridization. Next is sp2 hybridization, where 1s and 2p orbitals combine to form 3 sp2 orbitals. This type results in a trigonal planar shape with 120 bond angle. BCl3 shows this shape. Now let's look at sp3 hybridization, where 1s and 3p orbitals combine to form 4 sp3 orbitals. This results in tetrahedral geometry with 109.5 degree angles. In methane, all 4 orbitals bond with hydrogen atoms, forming a perfect tetrahedron. In ammonia, one of the sp3 orbitals holds a lone pair, creating a pyramidal shape with a bond angle of 107. In water, 2 lone pairs reduce the bond angle to 104.5 degree, giving it a bend or V shape. When elements have a d orbitals, they can create even more complex shapes. For instance, in sp3d hybridization, 1s, 3p and 1d orbitals combine forming 5d orbitals. Phosphorus pentachloride adopts a trigonal bipyramidal shape with sp3d 2 hybridization, like in sulfur hexafluoride. 1s, 3p and 2d orbitals combine to create an octahedral shape. Molecular orbital theory was developed by F. Hunt and R. S. Millikan in 1932. they introduced a way to weave electrons in molecules similarly to how we weave the electrons in atoms. Just like atoms have atomic orbitals where electrons reside, molecules have molecular orbitals where electrons move under the influence of multiple nuclei. Molecular orbital form when atomic orbital with similar energies and the right symmetry overlap. This is called linear combination of atomic orbitals or LCAO. When two atomic orbitals combine, they create two types of molecular orbitals, bonding and anti-bonding. The bonding molecular orbital has lower energy than the original atomic orbitals, which make it more stable. Electrons in bonding orbitals pull atoms together, creating stability in the molecule. Meanwhile, electrons in the anti-bonding molecular orbital have higher energy and increased repulsion between atoms, which destabilizes the molecule. Three conditions must be met for atomic orbitals to form molecular orbitals. Those are similar energy, same symmetry, and overlap. Molecular orbital can be sigma or pi orbitals. Sigma orbitals are symmetrical around the bond axis, while pi orbitals are not. The electron distribution in molecular orbital or electronic configuration helps predict molecular stability. To determine bond stability, we use the concept of bond order. Bond order is calculated as bonding electrons minus antibonding electrons divided by 2. A molecule's magnetism depends on whether it has unpaired electrons in molecular orbital. If all molecular orbitals are doubly occupied, it is diamagnetic, meaning it repels magnetic field. If molecular orbitals have unpaired electrons, the molecule is paramagnetic, which means it attracts to magnetic field. Now let us dive into the bonding of homonuclear diatomic molecules. These are molecules made up of two identical atoms like H2, He2 and O2. Let's explore how these atoms bond and the unique properties of each molecule. First, let's look at the simplest molecule, hydrogen. Each atom has one electron in its 1s orbital. When two hydrogen atoms bond, their electrons fill a bonding molecular orbital called sigma 1s. This gives hydrogen a stable single bond with a bond order of 1. With no unpaired electron, H2 is diamagnetic. Its bond dissociation energy is 438 kJ per mole and the bond length is 74 picometer. Now let's look at helium. Each helium atom has a complete 1s orbital with 2 electrons each. In helium-2, these electrons fill both the bonding sigma 1s and anti-bonding sigma star 1s orbitals, cancelling each other out. The bond order of He2 is 0, making it unstable. So He2 doesn't exist under normal conditions. Now to lithium. Each lithium atom has electrons both 1s and 2s orbitals. When they bond, the electrons in the 1s orbital form a closed K cell written as Kk and the 2s electrons enter the bonding molecular orbital. With a bond order of 1, lithium-2 is stable and found in vapor form. It is also diamagnetic since it has no unpaired electrons. For carbon, things get interesting. Each carbon atom has 2p electron and they form a double bond, but in an unusual way. Both bonds are pi bonds due to the configuration of electron in pi2px and pi2py. With a bond order of 2, C2 is stable and because it has no unpaired electron is diamagnetic. This unique double bond arrangement occurs because of the way electrons fill in the pi orbital in C2. Now for oxygen atom has 8 electrons and when they bond they fill bonding and unbonding orbitals including 2 unpaired electrons in the antibonding orbital. This gives O2 a bond order of 2 making it stable with double bond. However, because of its unpaired electron, O2 is paramagnetic, which means it attracted to magnetic field, a fact that's been confirmed experimentally. Hydrogen bond form when hydrogen is covalently bonded to highly electronegative atom like nitrogen, oxygen or fluorine. This shifts the electron density, giving hydrogen a partial positive charge and the electronegative atom a partial negative charge. The partially positive hydrogen can attract another electronegative atom, creating a hydrogen bond, though weaker than covalent bond. They significantly influence molecular properties. In hydrofluoric acid, hydrogen bonds form between different heights of molecule. In water, each hydrogen can bond with oxygen from neighboring molecules, contributing to water's unique properties like its high boiling point. When hydrogen is bonded to an electronegative atom, the shared electron shifts towards the atom, making hydrogen highly electropositive. This polar molecule has a strong electrostatic attraction between the hydrogen and electronegative atom, leading to hydrogen bonding. There are two types of hydrogen bonds, intermolecular and intramolecular. Intermolecular hydrogen bond occurs between different molecules, like in water, where hydrogen bond creates a strong attraction affecting its boiling point. Intramolecular hydrogen bonds form within a single molecule when hydrogen is between two electronegative atoms, like in O-nitrophenol, influencing its stability. Hydrogen bonding strength varies with physical state, being strongest in solid like ice and weakest in gases. I hope you enjoyed this video. Subscribe this channel if you only believe this channel can increase your productivity. Don't forget to share this to your friends so that they can save a lot of time. Until I see you in next video, this is RJK.